Myself, Dr. J.Arockia, ARULDOSS, PG and Research Department of Mathematics, St.Joseph's College of Arts and Science, Autonomous, Cuddalore. Today, I am going to take a theorem and definitions for third year mathematics students of 5th semester from Unit 5. First, we see some definitions related to the theorem. First one is ideal. A subset ideal of a commutative ring R with unity is called an ideal of R if it satisfies the following conditions. First one is I should be a subgroup of R under addition. That is, for some 0 belongs to I, and if A comma B belongs to I, then A minus B should belongs to I. And the second one, for every R belongs to R and A belongs to I, we have RA belongs to I. Also, AR belongs to I since R is commutative. And the second definition is maximal ideal. An ideal M of R is called a maximal ideal if M is not equal to R and there is no other ideal I such that M is contained in I contained in R. Equivalently, M is proper and whenever M is subset of I, then I should be equal to M or I should be equal to R is called the maximal ideal of R. Using those definitions, now we see a theorem. The statement is if R is a commutative ring with the unity and M is an ideal of R, then prove that M is a maximal ideal of R if and only if R by M is a field. Proof. Since it is an if and only if case, first let us assume M is a maximal and we have to prove that R by M is a field. We know R by M is a commutative ring with a unity 1 plus M. So it is enough to show that every non-zero element of R by M is invertible. For that, let A plus M should not be equal to 0 plus M. So A not equal, does not belongs to M. Consider our I is equal to RA plus M such that R belongs to R, comma M belongs to M. Then I is an ideal of R and M is contained in I. Since M is maximal, our I should be equal to R, hence 1 belongs to I. So there exists R belongs to R and M belongs to M such that 1 is equal to RA plus M. Then R plus M into A plus M is equal to 1 plus M in R by M. So A plus M is invertible, thus R by M is field. For the converse part, let us assume R by M is a field and we have to show that M is a maximal, that is, no ideal lies strictly between M and R. Since R by M is a field, we know that M is not equal to R. If I is an ideal with M contained in I contained in R, choose some A belongs to I minus M, then A plus M which is not equal to 0 plus M. So it has an inverse B plus M in R by M. Thus, our A plus M into B plus M is equal to 1 plus M, which implies AB plus M, which is equal to 1 plus M. This implies 1 minus AB belongs to M, which is contained in I. Therefore, AB belongs to I, so 1 belongs to I, implies I is equal to R. Thus, M is maximal ideal and thus the theorem is proved. For the second theorem, we see the definition of integral domain. An integral domain is a commutative ring with the unity 1 which is not equal to 0 having no 0 divisors. Formally, for some A comma B belongs to D, if A be equal to 0, then A not equal to 0, A equal to 0 or B equal to 0. For these examples are set of all integers and set of all polynomials over rational numbers. Next we see the definition of field. A field is a commutative ring with unity in which every non-zero element has a multiplicative inverse, such that for every A belongs to F, if A not equal to 0, then there exists B belongs to F and AB equal to 1. And we move on to the next theorem, that is a famous theorem called embedded theorem. The statement is every integral domain D can be embedded in a field F, or there is a field F and an injective ring homomorphism from D to F. Proof. For the proof, let us consider S be a set of fractions such that S is equal to, in a set A comma B, where A belongs to D comma B belongs to D, which does not contain 0, each pair A comma B represents a fraction A comma A by B. We define equivalence relation on D such that for A comma B is related to C comma D if AD equal to BC in D, satisfying the properties reflexive, symmetric and transitive. We know that the equivalence relation should satisfy these three conditions. Assuming that D satisfies the equivalence relation conditions, now let us move to let us define an operation on fractions addition where A comma B plus C comma D is equal to AD plus BC comma BD, and for multiplication if A comma B multiplication C comma D equal to AC comma BD. It is understood that this addition and multiplications are well defined using cancellation laws. Now our claim is D is a field. That is to prove D is an abelian group under addition and multiplication. Under addition, additive identity is 0, 1, and for multiplication, additive. Now claim embed D into a field F. For that, let us define a function psi is from our next claim is embed D into a field F. For that, let us define a function pi is from D to F such that pi of A equal to A comma 1. Clearly, pi is homomorphism. For some A comma B in D, pi of A plus B equal to pi of A plus pi of B. Also, pi of AB equal to pi of A into pi of B. Now, pi is 1 to 1 as phi of A equal to pi of B implies A equal to B, hence D is embedded in F. Hence the theorem is proved. Thank you.